Hi everyone, this is the last video now in chapter 6. The previous one was the mammoth one. This one won't be quite so big. The previous one, of course, was where you practiced all the really important types of questions. That was making sure that you properly got your head around this whole topic. So what we're going to do now follows on from it. Doesn't really teach you anything new. It's just looking at applying what you did using numbers to when everything is unknown. So what we're going to do this time, you see, is deal with an unknown velocity, an unknown angle, an unknown distance, and see what general formulae we can derive by looking at this scenario. So let's take, for our first example, let's take completely standard projectile motion, starting from a point A on a plane and ending at a point B on the same horizontal plane. So to be really general, we're going to call our initial velocity u. We're going to say it goes at an angle alpha to the horizontal. And we're going to first of all find an expression for the time of flight, which we're calling capital T. So from A to B, we'll set up our suvat. So from here to here, we have a horizontal distance x. Do you know what I'm going to do actually? Part B, I'm going to jump ahead here. Part B talks about the range of the flight r. That's what I'm calling x currently. So I'm not going to call it x, I'm just going to do this ready for part B. So x is the range of flight horizontally, and vertically from here to here there's no change, is there? So our vertical displacement is 0. U, we do, as always, our horizontal component, u cos alpha, and our vertical component, u sine alpha. Always the same, never changes. V, well, that's the speed we hit the ground at here. For what we're doing for this example, I'm not interested in it, so I'll leave that blank. A is always 0 minus g, because as you remember, anything going upwards is positive, but vertical acceleration due to gravity comes vertically downwards into the earth. And the time of flight is the thing they're asking us to find, and they're calling it capital T. So S, U, A and T is this equation. S equals ut plus half AT squared. Let's fill it in. R0 equals u cos alpha, u sine alpha, capital T, plus half 0 minus g, capital T squared. So I've just filled in everything from the suvat into that equation. So if it wants us to find the time of flight, well, if we look horizontally on the top row, we've got obviously we've got all the unknowns here, but we've got r involved, and that's not necessarily going to help us with what we need here. So, is it? Let's go vertically. Let's take the second row. So 0 equals u times sine alpha times t. So I'm going to put the t here, just so that the sine alpha goes last, because that tends to be conventional. And then minus half g t squared. Now, in order to find the time of flight here, I've got a quadratic equal to 0, so I'm going to factorise t out, because that's the one I'm trying to find. And that gives us u sine alpha minus half g t. So I have two solutions to this quadratic. One solution is t is 0. So that's telling me that I have a vertical displacement of 0 when time is 0 at the start. So that's obvious, but that's what that one is coming out as. And the second one comes from this equal to 0, doesn't it? So we've got u sine alpha minus half gt equal to 0. So we're going to make t the subject of this now. So take this bit to the other side. Multiply the 2 to the other side. And divide the g down. And we get that the time of flight is 2u sine alpha over g. And that's a general formula for the time of flight. So provided you know the initial velocity and the angle of projection, you can calculate the time of flight by plugging everything into this formula here. Let's do the same thing for the range of the flight now. This time I'm going to use the top row because before I used the bottom row. So from the top row, which is the horizontal motion, I get R equals U cos alpha t I'm going to put the t there, ut cos alpha, and then plus half times 0 times t squared, so that just goes. So we've got ut cos alpha. Now, using my t formula from part A, this 2u sine alpha over g, I'm going to plug that in. So u times by 2u sine alpha over g times by cos alpha. So let's just make that really clear. This t here, that's this bit. Let's work with this. Multiply out the brackets, so multiply the u and the cos alpha by the top of the fraction. So we get 2u squared sine alpha cos alpha over g. Now, I want to point something out to you here from your pure maths. You should recognise this 2 sine alpha cos alpha, because that is your double angle formula for sine 2 alpha, which means we have u squared sine 2 alpha over g. So yet again, if you know the initial speed and the angle of projection, you only need those two things in order to work out the range of the flight. So that's the first part done. Second part then, this is a general formula now connecting y and x, which are the horizontal and the vertical distances from where you start. So again, we're just dealing with a standard projectile motion, going from there to there. In the question, it tells us that it's... Okay, we'll look at that in part B, don't worry. So we won't give these points any particular names. I'll just stick with A and B. Again, we have a general speed of projection of u at angle alpha. And we, at any point along this journey, let's take, say, that point there. That point has a horizontal distance, x, and a vertical distance, y. Now, those distances there, x and y, because they are variable, this can represent any point along the motion. Like I could have marked the point here if I'd wanted to and called that x and that y, and the same with any other point along this curve. So the fact that I'm using unknowns means it represents any point along this curve here. What we're going to do ultimately for this is we're going to find the equation of this parabola. You know how something like y equals x squared is the equation of a parabola that looks like that going through the origin. That would have equation y equals x squared, and you could find any point along that parabola using this equation. We're going to find the equation of this parabola, given that the origin is here at A. And we're going to show that the equation of the parabola is this beauty. So let's go for it. For our journey A to B, we have any points, sorry, not A to B, A to a general point, x, y. So for this journey, we have S equals x, y, because it's some horizontal, some vertical distance. U equals u cos alpha, u sine alpha. V, that's the speed we are going at this general point. So if I were to draw a tangent at the general point, that would represent the velocity there. I'm not interested in it at the moment. A is 0 minus g, and t, well, okay, t we'll just call t because we don't know that one. So S, U, A and t. Let's write out our equation. S equals ut plus half at squared. Now, for S we'll fill in xy. For u, we fill in u cos alpha, u sine alpha, times t. For a, we fill in 0 minus g, and then times t squared. Let's take each of these equations separately now. So horizontally, we've got x equals u cos, I want to write the t first, ut cos alpha plus half times 0 times t squared, so that's just 0. Vertically, we've got y equals ut sine alpha minus half gt squared. Now here's the thing, in this equation here, look at what I'm aiming for. I want to aim for an equation that has y in it and it has x in it, so I've got to combine these somehow. It's also got u in it, so that's okay, and it's got alpha in it. What it doesn't have that these have is t. There's no t in this equation here, but we have t's in these. So we want to combine these but eliminate the t. So what we have to do is the principle of simultaneous equations, where we substitute one equation into another one, but we want to make sure we eliminate t. So first of all, to make this really clear, I am going to label this equation 1 and this equation 2. And I'm going to rearrange equation 1 to make t the subject. So t is equal to x over u cos alpha. Now I'm going to sub this into equation 2. So everywhere I've got a t in equation 2, I'm going to replace it with x over u cos alpha. So we have y equals u. I'll put the sine alpha next and then the t here. So I'll put the sine alpha there. The t will replace with x over u cos alpha, like that. And then minus a half times g times, this time we've got to square it. So x over u cos alpha squared. Now we need to do some work with this and tidy it up, and when we do that we will eventually end up with this equation here. So let's have a look. We have got y equals, I'm going to get rid of the brackets, so I'm going to make this into a single fraction, so this u sine alpha multiplies with the numerator. So we've got u x sine alpha over u cos alpha. And then the same here, the half and the g will go in the numerator, but I've got to remember to square this fraction first. So, well, I say the half and the g. The 1 will go in the numerator, the 2 here from the half will go in the denominator, won't it? So we have got gx squared in the numerator, and then in the denominator we've got the 2 from the half, and we've got this squared. So u squared cos squared alpha. Now we're really close. So what we're going to do next, I'm going to come up to here because I need quite a bit more space. I'm going to look at what I can tidy up and simplify. So you hopefully will have noticed that we've got a u in the numerator and the denominator there, so they'll cancel. But also here we've got sine alpha over cos alpha, and you know that that's the same as tan alpha. So the first thing we can do is say that y equals x tan alpha, and keeping an eye on what we're aiming for, look, we needed that. So we're getting there. Now we'll copy the minus. And then is there anything we can tidy here? Well, not specifically, but what I am going to do is write this cos squared in the denominator as sec squared. So we have gx squared over 2u squared, so that's this bit and this bit, but the cos squared there becomes sec squared alpha, like that, in the numerator. Nearly there. The only thing I need you to think about now is, from your pure maths, you have an identity that involves sec squared. You know that 1 plus tan squared alpha is the same thing as sec squared alpha. So I'm going to replace this sec squared with 1 plus tan squared. So gx squared over 2u squared, and then 1 plus tan squared alpha. And that was what we had to show. Look, y equals x tan alpha minus gx squared over 2u squared multiplied by 1 plus tan squared alpha. Why did we do this bit of work? Once we got to this point here, why did we do that, replace it with sec squared and then with 1 plus tan squared? Mainly because then we're only dealing with one trig function here, with just tan. And it tidies it up if you've got the same trig function throughout. So this here is the equation of the parabola. In terms of looking at it, it might seem a bit confusing at the moment. So what I'm going to do to try and highlight how it's the equation of a parabola is to highlight how, you know, any parabola has this form. Let's do it in a different colour. In fact, no, I'll do it like this. Y equals a x squared plus b x plus c. You know that any parabola looks like that, don't you? And look at this one. Y equals, here's our x squared. So let's write that bit first. But everything that's around multiplying the x squared, I'm going to put in orange. So minus g over 2u squared. Let's put our x squared there. And the 1 plus tan squared alpha, all of that is multiplying the x squared. So all of this together is your a. And then we've got our bx, which is our tan alpha x. That's there. And then there's no term on its own, so our c is 0 in this case. So you can see that it is actually an equation of a parabola. And notice how the leading term, the x squared term, has a negative coefficient. This minus g over 2u squared 1 plus tan squared alpha, all of that is negative, which is why the parabola is upside down, for want of a better phrase, because you know that when a is negative, the parabola goes this way round, don't you? So we have the general equation of that parabola there. And again, the only things we need to know in order to define this parabola perfectly are u and alpha. So we need to know the speed we project at and the angle we project at, and that's it. And we can say everything else we need to about the parabola from that. Now, using that, it wants us to answer part B. So the only thing I'm going to do before I even look at part B is I'm going to write this equation down again. So our equation from before, let's just put it to the side here, was y equals x tan alpha minus gx squared over 2u squared 1 plus tan squared alpha. You'll be pleased to know you don't have to memorise this. It's just you do need to be able to know how to derive it, like I just showed you. So now we've got an example with numbers. We're told that u is 28. Alpha is still unknown. But what we do know is that at some point along the projectile motion here, which is a particle being projected from a point O on a horizontal plane, it tells us in the question. So we've got this situation going on for a point O. U is 28. Alpha is unknown. What we do know is that at some point it passes through a point B. And B is where we've travelled 32 metres across and 8 metres up. Now, I don't know whereabouts on the diagram 32.8 falls, because I don't know the full range of flight. I could work it out using one of the formulae that I've just seen. I'm more just thinking for sketching this, I don't know, I really don't know where this point is. Is it somewhere over here? Is it there? Let's just put it randomly here and hope that that's about right. So this is assuming that we've gone 32 metres across and 8 metres up. Now, knowing all of that, it wants me to find the two possible values of the angle of elevation alpha. So let's work with it, shall we? So that's O, this is B. For O to B, we'll set up our CVAT. (28 cos alpha, 28 sine alpha). V, I don't know the speed. If I were to draw a tangent there at B for the speed, I don't know what that is. No idea. Don't need to know it either. 0 minus G, and the time is T. But, see, this is the way I would normally approach it. What I'm going to do, however, let's just put here, let's put normal way. What I'm going to do, however, because this is a part B and we've just worked out this equation, is we're going to use the alternative way. And that's using this, y equals x tan alpha minus gx squared over 2u squared 1 plus tan squared alpha. So let's work with it and see what happens. So this here is xy, isn't it? So we've got 8 equals 32, tan alpha, alpha is our unknown in all of this, minus g times 32 squared over 2 times 28 squared, and then 1 plus tan squared alpha. Let's do some tidying up. Here, I want to work out what this number is. So, g, 9.8 times 32 squared over 2 times 28 squared, 6.4. So I've got minus 6.4 times by 1 plus tan squared alpha. Now let's expand that bracket. So minus 6.4 minus 6.4 tan squared alpha. This is looking like a quadratic equation, but this time in tan. So let's bring everything to the left-hand side. And we've got 6.4 tan squared alpha minus 32 tan alpha, and then 8 plus 6.4, it's going to be 14.4, equal to 0. So let's solve the quadratic equation just using our quadratic solver on the calculator. We've got A is 6.4. B is minus 32 and C is 14.4. That gives me tan alpha is 4.5, or tan alpha is a half, 0.5. So from this one, make sure I'm in degrees and not radians. I was teaching pure before, so I'm trying to answer these and I was stuck in radians, so let's make sure we're in degrees. So inverse tan of 4.5 gives me an angle of 77.4 degrees there. 77.5, sorry, rounding to 3 significant figures. Or, for the other one, inverse tan of 0.5 gives me an angle of 26.5 degrees to 3 significant figures. Now what's going on here? Why have we got 2 possible values of alpha? Well, it's because of my initial my initial ponderings about where to place this point B, where it's this displacement here of 32.8 from the start, because what's happening is this. At that speed and at 2 different angles, we could go through that point, because we could either have the motion looking like this, where we go at an angle of 26.5, because that's quite a small angle, isn't it? Something like this. Or if we go at an angle 77.5, that's shooting it up much more steeply, and it looks more like that. Both of them pass through this point B, like that. So we have this one has the angle of 26.5, or this alternative has the angle of 77.5, both of which pass through the point, which is a horizontal distance of 32 and a vertical distance of 8 up from O. So there were 2 possible scenarios that could fit the information we were given. Now, if you had tried to solve this the standard way, using S, U, A and T, you would have ended up with exactly the same 2 possible answers, using S equals UT plus half AT squared. And you'd have still got to this point. Don't forget, this equation in part A we derived using S is UT plus half AT squared. So we basically did the work required for solving this the usual way but with unknowns before then plugging in what we did know to this. So we just did it an alternative way round. So there we go. Now you can do exercise 6D, and that is the entirety of the Projectiles chapter, which I hope you'll agree with me at this point is the best chapter in the book. Have fun, and I'll see you soon.